Okay, first, before we start, I want to just make an overview of how many classes we have left. We don't have many. Okay, we have next Tuesday and Thursday, so that will be the 4th and the 6th. And then after Easter we have, so let's see, it will be, there are no classes on the 18th, so we have on the 20th will be the next session. And I'm traveling yep, I'm traveling. Yeah, and we, in theory, we should have one more class, which is the 25th, but I'm traveling on that week to Brazil, some conference. So we won't have classes, so we will finish up by the 20th. Okay, so that's the plan. We have 3 classes left. Okay. Okay, not much. It went like that. Okay, I was planning to give you more information so you can, stuff your brains, but now I missed my chance. Maybe it will be next year. So the idea is next class will be on multi-phase boosting, subsea boosting. Okay, for that I hope it doesn't take much time, because we will use some of the same philosophy that we are going to present. We have been presenting last class and today about pumps. Then on the 6th we are going to talk a bit about production optimization. And then on the 20th we will have kind of the wrap-ups, any particular topics that are relatively short and that we can just to make you aware of them, and the kind of the overview, and then if you have any questions about the exam. Okay, so that will be kind of the final or what I call course wrap-up. Okay, any question? What else? So we have, I think, the deadline. So the other exercise, you should have enough by the end of next week to start working on it. So we have 2 choices. Either I publish it before Easter, and then you have Easter to work on it, or I publish it after Easter. But anyhow, I will give 2 weeks after Easter to make it, no matter which one of the 2 options. Okay? So let's see, 2 weeks after Easter, I think the date was, so it will be someplace by the 7th, I think. That was what we agreed last time, 7th of May or 5th of May. Okay, but I will hopefully have it ready by the end of next week, so you can, those of you who already finished with number 4, you can start working on number 5. Okay, and if you're not traveling anywhere, or if you're just going to spend time with your family, or okay. I'm not saying that you should, but we have different plans, so because don't say later that I'm enslaving you. No, that professor wants us to work during Easter and he's so mean. And no, I'm just saying you're free to do what you want. You will still have 2 weeks, but you can have 1 extra week if you work on Easter. Okay, so let's talk about last class we were talking about ESP, and that's a picture of the guy. I forgot the name, but it's not so simple either. Armais Arutunov. Okay, he actually was born in Armenia, I think. That was Russia. A serious guy, and then he moved to Oklahoma, and then he started making this, and I'm not sure which company it was. I think it was called initially Reda. That is a famous ESP manufacturing company, and that was later on bought by Schlumberger. Yeah. And you have main manufacturers of ESPs. You have Schlumberger, you have Baker Hughes, and you have a company called Wood Group, and there is one more, but I don't know. These are the biggest, but one of them, the main inventor, the patent, everything, was the first one to try to put the motor and the pump inside the wellbore, and that really make a huge difference in production. Okay, so here was more generalities. I guess you had some theory about pumping, so that's not completely foreign to you, but it looks like just like an inflow, okay, and available pressure curve, which makes sense. It's like something that gives energy to, and it makes sense also that when we increase the flow, we need the delta P will be less. Okay, what can reach is less. We also saw what happens with frequency, how we change frequency, and how we scale the equation. Basically, we say that the head is scalable with the square of the frequency ratio, and also the rate is, is also proportional. The ratio between the rates is proportional to the ratio between the frequencies. And I say that's not very, it's not the most, I would say, popular option to do in subsea wells. Why? Because you have to intervene at least, I think the longest might be around 2 years. Okay, but if you have problems at 6 months, then you have to go make intervention, and it's a big thing. Okay, make intervention subsea to change something. Remember that pump is screwed in part of the tubing. Okay, so we don't have a picture of. I think we had a picture someplace. This typical well that you have to remember to sketch it also by. Okay, someone wakes you in the middle of the night, make a well with a DSP. You have to be able to do it with. Okay, that picture. So it's really screwed. It's part of the tubing. So to pull it out, to make maintenance, to observe what happened, you have to pull the whole thing. You have to take out Christmas tree. You have to take out the tubing hanger. Then you have to take out the tubing. So it's a big operation. You have to kill the well. You have to put a plug. It's a big operation. Okay, so it's something we don't want usually. It's not very popular, unless, and we are going to discuss about that case. We have an exercise now in class that is when you have a dry Christmas tree, when you can have a drilling module, and then you can have access intervention to the wells whenever you want. And it's also very important when you have low GOR, heavy oil, for example, and when you have large amounts of water. Okay, so let's. So first, I want to show you just a picture of this penetrator that I told you that is in the casing hanger, tubing hanger. Okay, so here you see that's the tubing. The hanger is the gray part, and then you have the penetrator that goes. It's a hole. Okay, it's like you could say it's a potential leak path. Okay, where you have the cable going from outside. Here you have this variable speed drive. You have the main transportation line for electricity, or a diesel generator, and goes inside the well. Okay, there are many, and this is for a very simple well, onshore well. For when it's subsea, it's more complicated. Yes. So now let's. Okay. So now. Okay, something that we have seen so far. What kind of. So first we say limitations so far, operational limitations of ESPs. Okay. So one of them is the frequency. Okay, frequency has to be between usually 30 hertz and 60 or 70 hertz. You can take it all the way to 70, maybe. I think hertz is with capital H. I think. Is it? Yeah. Yep. Okay. Then the other thing we said is that the P at the suction has to be greater by a factor times the bubble point pressure. Okay, we don't want to have any gas in the pump. It's detrimental for the operation of the pump. There are some, we will see at the end now, that there are some new models of pumps that they try to make it gas friendly, that you can go up to 10% gas, okay, or 30% gas. For that, the shape of the pump has to be changed dramatically, okay. But we have, and people try to stretch the operational envelope of, but that's a very important requirement. So that requirement tells you that you either have to produce the gas through the annular if the pressure will be below the bubble point, or that, especially in offshore, that you have to produce all the time above the bubble point pressure. And that's a very important, and we will see it in our exercise today. So let's continue talking about limitations. So one thing is that, okay, let's put this delta H versus Q, and that curve that looks something like that. Okay, for now we are going to focus just on one particular frequency, frequency 1. Do you remember what was the power of the pump? How do you calculate the power of a pump? Delta P, so P, that would be P discharge minus P suction, right, times the Q, okay, and the Q, that's in local conditions, and these units have to match conditions, okay, and then you have something else, okay, that's exactly what we are giving to the fluid. That's how you compute the change of energy of the fluid when it comes in and out of the pump, okay. But on top of that, the pump is using much more energy because you have some losses. In any process that you want to change or give energy to the fluid, you cannot give 100% of the energy. You have to waste a lot of energy just to give, and we will see now where it comes from. So you have one term called hydraulic efficiency, right? That sounds familiar. And then you have another term called mechanical efficiency. Sorry, this should be divided, right? Okay, mechanical hydraulic efficiency times the mechanical efficiency. And the hydraulic efficiency is basically because of many reasons, and I don't want to dwell too much into it, but it's basically because fluid friction, okay, friction between the fluid and all the walls that you have that might be stationary and might be rotating, okay. And yeah, and another thing, let me just pull that image that I think is very, very nice. Okay, so you see you have the same head versus flow rate, and that's usually how the hydraulic efficiency goes, okay. You have one rate. At that particular rate, that is what we call the best efficiency point, at that particular rate. And at that rate, what happens is that when it's yeah, maybe I can yeah, when you have certain rate, the fluid, you have some I think I showed before how, not in this, not here, but here, okay, you remember it's something like that, right? And the fluid goes first perpendicular from the top, and then it goes and spreads radially, right? When it enters at certain rate, it has to be completely aligned with this angle that you have, okay. If it's not aligned, if it's inclined on deviation on the other side, it will start, the fluid will separate, okay. It's like, if we are going to make kind of a very, okay, if that's the we call it the blade, or one of the blades of the pump, if we're exactly like that, that's fine, the fluid will follow exactly the profile of the blade, okay. But when we are like this, then what you have, okay, is that the fluid will start to detach here, okay, and create all of these eddies, and the eddies cause loss in energy, okay, loss of energy because of all of this. So you can see that very clearly. That's actually measurement, okay. They measure it with particle image velocimetry. You don't have to know what it is, but that's actually measured. And you see at the best efficiency point, the lines follow exactly the path between the two blades, exactly, without anything. But then when you move and change the rate, that means that the angle changes, and when the angle changes, you start getting these circulation areas. Okay? Yeah? So just the conclusion is that you have one rate at which you have the best efficiency, that you have designed your blades for. When you go outside that rate, either above or below, the efficiency will start to go down immediately. Okay? Okay, so that's, keep that in mind, that the efficiency curve is something like that. And actually, when I so let's put that image here. I have delta H versus Q, and I have my curve here, and I have that curve that does something like that, the efficiency curve. Okay. And actually, when I change the frequency, so that will be a frequency 1. When I go at a different frequency, frequency 2, the curve will move slightly to the left. Okay, that efficiency curve will move to the left. Okay, so now the best efficiency rate will be shifted to the left. Okay, but you don't have to worry too much about it. Just know that for each frequency, the maximum efficiency is shifting. Okay, and of course, we always try to be close to that rate. Okay, if you're going to design a pump, that's going to be the rate that you want to produce from the well. You want that rate will coincide with the best efficiency point of the pump. But sometimes we will see it's not very simple. We cannot ensure that we will be all the time at that point. Okay, and we will see for several reasons why. Now there are some things, so maybe I can show you that. Okay, that's some people were asking how it looks like. Okay, that's a relatively small ESP, but there you have the impeller. Okay, I cannot open it, but it has, so the fluid, it should be located like that. Okay, the fluid is coming through that direction, that rotates, and then the fluid comes through this side. Okay, that's rotating, and the fluid comes from that side. Yeah, and here you have, if I take out that cover, I will see exactly those blades that I showed you before. Then you see we have one part that I told you is the diffuser. Okay, then the fluid goes exactly out and then comes back again in this diffuser. Okay, this diffuser again is a series of blades that they expand, so the area when you enter is small and the area when you go out is big. Okay, and they redirect the fluid from, if you see here, they redirect the fluid actually through the other stage. Okay, through this small disc. Yeah, more or less. So I'm going to pass it around so you can see. Some things to note. Okay, you see how, so this is missing what is driving this impeller. Okay, all of that is fixed in place, and this one is rotating, right? So what is giving the motion to this is an axis that goes through all of them, but the axis is free to, the axis is in place, and this is free to go up and down. Okay, so you need, if you see here, you have an area which is a washer that is going to be in mechanical contact with this part. Okay, yeah, okay, and we will see that that's called a rotating impeller, floating impeller. Okay, so it has it depends how is the flow, how big is the flow. If it's very low, it will be just laying down, rotating, but laying down on that face. If the flow is very high, it will be pushed up, and then it will make contact in this upper area. Okay, so it's like rotating, and the way it is fixed to the axis, you see, it has a small, it has a small slot. Okay, that the axis also has the same slot, and it has something, a small metal part that is making sure that they are fixed, the axis with the impeller. Okay, so I'm going to show it, and I hope with the picture will be a bit clear. Okay, so here is exactly what I'm showing. Okay, what I was trying to explain. If you are at the low rate, that means you are probably on the left part of the curve, then the flow doesn't make enough force or doesn't make enough pressure over the, here you see the impeller. Okay, this is what is rotating. So it will tend to lie, it will tend to be supported against that part. Okay, and of course when you have two parts that are in contact and you have them rotating, that makes a lot of friction, and friction makes wear, and wear eventually ends up in failure. Okay, so that's what we call down thrust, because the impeller is laying down on the support, on the hub of the pump. Now if we go to the other way, to the other side, to a very high rate, what will happen is exactly the opposite. Okay, it will detach from that support, but then it will start hitting on the support in the back. That you will see there is a small ring that is in the plate. And then again, you have again wear against a lot of rotation, a lot of heat, a lot of wear, and because of that you have failure. So that's why you cannot be operating at either at a very high rate or either at a very low rate. You have to be within a range where you have like a contact small enough such that you don't have important wear, so you don't accelerate the normal failure, the normal lifetime of the pump. That clear? Yeah? So that's just to show you, the only thing is just to show you that you are for each frequency you have to be within some maximum rate and a minimum rate. Okay, that you have to operate. So I think I had a thing is that. To be, you can put the animation also if you want. Okay, and I have to be, so I define a region where I will have kind of an expected, if everything else is the same, if everything else it's okay, I will have kind of a normal life of the pump. Okay, otherwise I will have too excessive wear here, and then yes, so I think here we have another nice figure, okay, that is showing something like that. Okay, where, and if you exaggerate the distance between the impeller and the shroud, it looks something like that. Okay, so that's why really in theory, in theory we have this very big range that we can use, okay, in theory, but in practice I cannot. It's really not recommended that I operate below that and that I operate above that. It's not recommended. So I limit very much seriously my operational envelope of the pump. Okay, and for different frequencies, that's how the curves go. Here I have, that will be my Q minimum and Q maximum. So those are the main two reasons, okay, to avoid up thrust and down thrust, and to avoid too low efficiencies when I increase or decrease too much the rate. That's the two things. But that's why, I could just tell you the pump has two lines, that's all, remember it, but I hope now you keep it, you know the reason, so it's easier for you to remember in the future. Okay, why do you have these two lines? Okay, it's a low efficiency, you have this separation phenomena, and also you have the up thrust and down thrust. And with frequency it goes like that. So at the end, I think we have some picture here from the Peregrino ESPs. Okay, that was taken from a paper. Okay, at the end the area looks something like that. Okay, and that's why it looks like that, because you have Q max, you have Q min, you have maximum frequency and minimum frequency, and that makes you a very nice little box where all the Q delta P points have to be inside that point. Okay, so for example, you go and you run your simulations. Okay, and you say, okay, I want that particular combination. So I have to find a pump that exactly will cover all of them. Okay, and hopefully that's something that we wish, but not sometimes, that it will be. You remember this efficiency? The efficiency, also you have a line that goes a bit, sometimes can be closer to the minimum. It's called BEL, best efficiency line. Okay, and it's telling you that's the rate. You remember where I had the maximum in. You remember the curve of efficiency does something like that. So that's where I have the maximum. Then if I reduce the speed, I will have it a bit more to the left and so forth. So also that line, I should be operating relatively close to that line. So that means that if I have two pumps, okay, one of them that is maybe like that, very big, okay, and another pump which is maybe like that, also again very big, okay, I will try to use, for example, this pump, the, how do you call this color? Magenta? Yeah. My wife will be proud of me, huh? When my wife is asking always, you cannot see the difference. No, I say, for me it's like red and pink. It's not pink. Okay, so we get into a small discussion, but now she will be proud. Okay, so we try also, if possible, that it will be close to a good efficiency. Okay, because we want also to save. Okay, then one thing, okay, that also where I have a constraint. So you see the operational envelope usually is like that, the suction pressure above saturation pressure. And also one more thing is that the maximum capacity, power capacity of the motor. Okay. So the motor usually can be anything between 100 horsepower to 1600. That's a very huge pump. Okay, and you have to be sure also that that power that you calculate, that is equal to delta P Q over hydraulic and mechanical efficiency, that one has to be all the time less or equal than the maximum power that I have installed. Okay. And first, it's expensive to get a pump with a bigger motor, and then also it's bigger, the motor. So for example, if I want to put 1,000 horsepower in a very small casing well, okay, it won't fit. It won't go through the casing. So those are another requirement that we have to care. And then there is another one that is called cavitation. Okay, and that is if we take the pressure, and that will be kind of the distance along the fluid or in the flow path from pump inlet to pump outlet. Okay, initially just the fluid to go, I think I had an animation but I could not find it. It's here. Okay. Initially, when the fluid goes from the inlet all the way to the blade, it's going to have some losses. Okay, so it's going to have a drop in pressure, and the velocity is going to be increased very much because the channels are going to be made very narrow. Okay, because of that, you're going to see a behavior, something like that. Okay, initially it's going to reduce, and then it's going to increase and increase and increase until the pressure reaches the suction pressure, the discharge pressure. Okay, and exactly in this path is very critical that here we don't reach the it's called the bubble point, but the vaporization pressure of the fluid. Okay, because we have that phenomena called cavitation. Cavitation, the fluid close to the wall vaporizes. Okay, becomes vapor, but then later on it will have it will be it it will have again higher pressure. Okay, so it's going to re-condense again. It's going to re-liquefy. But when it does that, let me just show you the picture. That will be more. Okay, so in this case they are doing the same, but they have a small electrode, and they are giving a small charge to make it vaporize the bubble. Okay, and you are very close to a wall. So when the pressure goes down, you reach vapor bubble point. Okay, and you see after the pressure returns to a higher level how it hits the wall. Okay, in the collapsing, it causes, like this collapsing process causes a jet of fluid to go and impinge on the wall. Okay, and that's what we call cavitation. And because of the repeated with time, the repeated effect of all of these droplets collapsing on the wall, we have again wear of material, and we are going to be losing part of the blade. Okay, so that, I think we have some pictures. It's not exactly from an ESP, but it's okay, that. Okay, you see how the damage can be okay in the blades of the pump. Okay, or again reduces the lifetime. Again, we have to pull out. We don't want to make interventions so often. And so that we do just by saying that P at the suction has to be greater than P limit. Okay, that is not the vapor, because it will have losses. You see that P is the P at the inlet, and you have to be sure, well, not P injection but P inlet. Okay, you have to be sure that is high enough such that you are far away within a safety limit, safety factor from that vapor pressure. Okay, and that usually, we don't want to go how it is done in practice, but usually manufacturers, they have something called NPSH, and just to make you familiar with the term, net present suction head. Okay, remember, pumps started with pumping just water. Okay, it's later that some crazy guy started to using for oil, for any fluid that you want, but people were working mainly with water, so they just say, why do we want to carry delta P for everything? Let's just carry delta H, and we know that density is 1,000. Okay, but then came people starting using oil, then people, so we all the time have to make the conversion. But that's, so the net present suction head is given in meters. Okay, and then I can change that to, with the density, change to pressure. Okay, to bar. And but we are not, just so if you see that term in one of the pump manuals or in the pump, you don't get, you don't know what it is. And usually, of course, if the Q increases, that NPSH is going also to increase. Why? When the rate is higher, you have more losses from this point to that point, right? So that's why you should have a higher pressure at the intake, because you have more losses from the inlet all the way to that point where you are sure that you have the lowest pressure and cavitation will occur. Okay. But you go, if you are in your company, go to your pump specialist and say, what is the minimum pressure you want to have in the suction? And they can tell you. Okay, so far so okay, so that's the place where cavitation occurs. Okay, we are almost finished with the, you see, why do we use pumps if we have so many constraints? It's like, we have this, no, you cannot do this, not that, not that. Okay, so that's the place where you the pressure is the lowest, so you have the chance. So here's pressure is the lowest, and then pressure increases again, and then you have cavitation. And it's like, you know, it's a small jet, but it's all the time is working all the time, making damage on the wall. So then comes the last thing that I want to say about pumps. Okay, well, the last thing on the restrictions, and is the effect of viscosity. Usually, the pump, okay, effect of viscosity. Again, if we are using water, these curves are usually created for water, even for ESPs. They come and test it with water. But then if you have, so that will be viscosity equal 1, right? The viscosity of the water. But then if you have another higher viscosity, the curve will look like that. Okay, you will have a reduction on the head that that pump can deliver. And it's because of all of these losses. Remember that the curve is like that because of all the losses. Okay, so that's viscosity that is higher than water. Okay, and also the lines are shifted, and we will see it now here an example. The minimum lines, they are shifted to the left, and also the maximum lines are shifted to the left. Also the efficiency is shifted. So at the end we end up with the point is that we end up with a very reduced operational region compared to what we had with just water. Okay, viscosity reduces the operational envelope of the pump. Okay, and if you remember, we are working, sometimes oil in reservoir conditions can be very kind, can be 0.3 centipoise, can be something even less viscous than water, but sometimes we're working with viscosities that they are 300 centipoise in reservoir conditions, 500 centipoise. So there, if you design your pump, you have to design it taking into account the effect of viscosity. Okay? And that so how to estimate the pump performance with viscosity. Okay, one way is to do testing, that you take it to a bench and you perform testing, lab testing. Or another way is to use, is the most how you say, extended method to calculate that, and that's called the Hydraulic Institute. That they took measurements for a lot of pumps, for a lot of manufacturers, for a lot of fluids, for different viscosities, and they try to compound and squeeze all of that in some correlations, in some plots. And I have programmed that for you in the exercise we're going to make, so you don't have to worry about it. But if you ever are curious or you need to use it in your professional life, usually they are pre-programmed in all of this software, in Prosper, PipeSim, they are pre-programmed for you. But if you need to know where it came from that model. Okay? But still people say it's not, you know, it's not 100% accurate. Okay? So people say, I have read papers, they say it's between 30% accuracy, 50%, 10%, so it depends really on the case. But at least it captures the main effect. Yes? Okay. So now, before I give you a break, and then we come back for the exercise, I just want to show you how it looks like when you want the pump, the ESP, to handle more gas. You see the traditional configuration to the left? Okay? It's very radial. It's very, the fluid goes through here, and then it goes exactly almost in 90 degrees. You can see it in the impeller you have there. The fluid goes and has to change direction quite dramatically. This is very good for increase in pressure. Okay, there you need you don't need many stages. Okay, but it's very bad for separation, because if you have some, let's say you have some bubbles in your main fluid, okay, the fluid will tend to go there, and the bubbles will tend to accumulate against the wall, and they will start to create pockets. Okay, like when you see, for example, your impeller under gas. Let's see if I manage to make it nice. Okay, you will see that you have some areas where you have an accumulation of these gas pockets. Okay, and because of that, that reduces the area, the flow area between blades, and that is detrimental to the efficiency. Okay, it's detrimental to the performance of the pump. While this other design, you see, it's called mixed flow. Okay, mixed flow means that it's a mixture between axial and radial. Okay, it doesn't go exactly, but it goes something in between. The main disadvantage is that the delta P per stage is usually low. That means that I have to put more of them to achieve the same delta P. But the big advantage is that it's very tolerant to gas. Okay, and when we say very tolerant, it's a GVF of GVF stands for gas volume fraction, and this gas volume fraction is at actual conditions or local conditions. Okay, and is around 10%. And that's a pump that you say is very tolerant to gas. Because you avoid the accumulation, you actually try to mix better the fluid with this kind of mix axial. Okay, why not put it exactly axial? There are some machines, like I told you, that the blade is something like that. Okay, and that's the hub, and then the fluid just goes, okay, completely axial. That's a very poor drawing, but okay, because then that doesn't lift too much the pressure. You have a very low increase per stage, so you will need a very, very large pump. When it starts getting very, very, very big, you have all of these problems with the structural, you had all of this bending, you have so those pumps, those that are called axial impellers, are not used in ESPs. Okay, so we take a break, 15 minutes. Any question before we go to the break? No? Okay. Thank you. Yeah, so one thing, there is people awake. I'm not, apparently I'm not awake enough. So you see, it shouldn't be, okay, net, maybe I was confused because of net present value. It should be net positive suction head, okay, NPSH, not present. Okay, net positive suction. Okay, so one thing I just found now on the web, how do you call that device? Okay, a key. And the main idea is that that's the axis that you have through all the rotors, and they have a key, and then you have the same opening on the impeller. Okay, and then the key is making sure that they are rotating at the same speed, that they are, like, it allows movement in the axial direction, but it doesn't allow movement in the, if the axis moves, then the impeller has to move. Okay, and that's called a key, just for general culture. Okay, so now let's, the exercise is in this directory, okay, the common directory where we have all the class files, and it's going to be on the Peregrino field. Peregrino is an offshore field operated by Statoil. It's offshore, almost straight out of Rio de Janeiro. Let's see, I think we have some pictures to show how it looks like. So there are two platforms, as I told you. When we have pumps, we want to have a way to make intervention. So we have two. Let me just put the other image right away. Okay, and here I think I should expand a bit more the image. But the wells, you see the idea, but the wells, one of them are drilled from this side to reach certain part of the reservoir, and the others are reached from that side. There you see the drilling tower where you can access every well and make intervention on them, also here. And also we have so we have oil producers, and the oil is relatively viscous. And we have water injectors that they are injecting just in the how do you say, in the outskirts, is it the name?
Flank of the reservoir.
Yeah, the flank of the reservoir, exactly. That's the name I'm looking for, flank. Good to have some reservoir engineer that can pull you out of trouble. And then later, so the system looks like I have all the wells, okay? I commingle the production of all the wells, and then I have a pump that pumps, well actually here I have the separator, but I commingle the production through a riser that goes to the FPSO, to the floating FPSO, where I have the main processing is done in the FPSO. Okay? And every well is producing, and they are almost at the same pressure, and this pressure in our exercise we are going to assume is 10 bar. Okay, because all of them are, it's like every well is producing to the same point. Okay, and I can control exactly the pressure of that point with the suction of this pump, and it will be 10 bar for us. Okay, so it's not a network, we don't have to solve a network, so we can look individually at each well. So I think the other picture I had was of how it looks like. What does LQ stands for? LQ? Living quarters. Yeah. Okay, water injection also there. And here is the layout of the well, and it has some things that we are not going to talk about completion. It's not the purpose of this course, but we are going to just to simplify, saying that we have, and it's deviated. Okay, it's of course deviated because we are drilling from the same place, and then to reach different targets we have to deviate. But we're going to assume just a vertical well, okay, for our case. We don't want to make it too complicated. And then we have RESP, and we have a packer here. Okay, and we have just a producing layer. And we are going to assume that from because here you have the inlet, the pump, actually the inlet is someplace here. Okay, that's the inlet of the pump. So you have some distance between, because the pump cannot go, that's another thing. All of that is rotating, okay? When you incline it, you will start to make contact between every part, okay? Everything starts to make contact. The axis with the inner part, everything. So the pump usually has a maximum inclination angle where it can work. It cannot work like that. Okay? It has to be all the time almost vertical or very close to vertical. So that's why we have to put it in the section where we have a good inclination in the wellbore. After that, the pump cannot go that low. Okay, so that H is what we are going to define here as the distance between perforations, H1, and then we have H2, which will be the height from the pump discharge to this point where we have fixed pressure. Okay. And you will say, okay, but here maybe the pump has also some length, okay, might be 100 meters. Okay, remember that we have to put usually 70 of these. Then comes the motor, then the gas separator, so you can really see that it can become huge very quickly. But usually that is neglected, okay? We just neglect the change in elevation due to the pump. Okay, so let's open the exercise. And I have tried to make as close as possible using data from a master thesis to make an example for the class. So let's first look at okay, so that plot, the one at the end, is what you expect to produce from Peregrino, the production profiles. And you have water that initially I'm not producing, but is increasing very rapidly. Then you have oil, which is decreasing from day one. And then I have reservoir pressure that is decreasing slowly because of the water injection. So we're going to make, so let's maybe make a comment here. Design process of artificial lift equipment. Okay, or we can just be specific and say that will be for ESP. Okay, remember I have someplace a reservoir department that he's going to say he has a reservoir model. Okay, so he has the rates of wells, that will be well I, okay, with time, every rate. Okay, and he has also a minimum flowing bottom hole pressure, right? That's how we know reservoir people work for each well. Okay, so from there he's going to obtain the production profiles that he wants, okay, versus time, Q. Let's say he found something like that, okay, and then gas and water, etc. And then he's going to go and ask, that's what he wants, that's what gives high recovery factor, that's what gives the revenue of the field that they want. But now they go to the production department, okay, and they go to the production engineer and they ask, can we deliver that rate? And if not, how is the equipment? Please design an equipment that allows me to deliver that particular rate. And the first thing they do, what the production engineer like to make, available versus required. Okay, so they calculate for each rate in time also the delta P that you have to breach with time. Okay, in our case it's relatively simple, everything is discharging at the same point, so we can say that's 10 bar, and we can very easily calculate the two curves, how they're going to change with time. But for a network it's a bit more complex. You know, the network starts playing the competition between the wells, etc. So just keep that in mind. But basically I say I have my IPR that is going to change with time, and I have my TPR that also might change with time. Okay, and I say I want that rate. That's what the reservoir engineer, my boss, told me. Okay, not my boss, but my colleague. So I want to deliver exactly that delta P, and then they try to find an equipment such that covers delta P, the pair that you gave for most of the lifetime. Okay, and with high efficiency. Okay, not gas at the inlet. Okay, and at affordable price. Okay. of course, this guy has a lot of pressure. Okay, on him, the reservoir engineer say, "Give me that. If you do that, I will be very happy, and the company will be happy." Production engineer then has to balance, has too many things. I have to cover for this, for that, for that, for that, for that, and at the end, of course, he says, "Okay, the outcome is, yes, I found the equipment. I select an equipment, ESP model, okay, to produce, for example, from time 1 to time 3. But for another period, I won't be able to produce that rate that you gave me. No chance. Okay, I didn't find with a unique pump, even by changing pumps, no chance. You will get, for some reason, the pump will be too expensive, it won't fit in the casing, it's too much gas, etc. So, but you cannot produce in this interval T, for example, 3 to T5. Okay, so they go back to the reservoir engineer and say, that's my conclusion, and the reservoir engineer again has to take those considerations into account, change again their analysis, generate a new profile, take it back to the production department, say, now are you satisfied? And that process forth and back many times. Yeah, more or less. So now we are sitting here. Okay, that's what we are in our exercise, and we are trying to see if we can fulfill what the reservoir engineer is saying that they want. Okay, so yeah, so here we have the main data. Okay, initial reservoir pressure 231 bar. That's the productivity index. We are assuming that it's producing just liquid. Okay, we are under saturated fluid. Then we have H1, that is the distance I told you from the reservoir to the pump suction, and H2 is the distance from the pump discharge all the way to the wellhead. Then you have the two diameters that you need to calculate velocity. The pump name is Centrilift 675, and Centrilift is from Baker Hughes and has 78 stages. So what do I have to make? Just available versus required. Okay, and then calculate delta P, and what I will try to make is see if it falls within the pump map. Yeah, so the first thing will be calculate available pressure at the suction of the pump, required pressure at the discharge of the pump, subtract them, okay, and then calculate the head, and then I'm going to plot the head in the map of the pump. And I'm going to do that from reservoir pressure 231 to 125, and assuming that the water cut remains constant. Okay, and I want to produce, the reservoir engineer said he's very positive, he's very optimist. He said, well, I want to have 1700 rate of oil in like a plateau mode. Okay, one more thing. So here you have, so let's go to the full description. Here you have the production profile of Peregrino. Then we have this emulsion behavior that I told you about. Okay, because we have a mixture of oil and water. If you remember, that was discussed in a long time ago in a galaxy far, far away. That you have the water cut, okay, and you have something called the inversion point. Here, when it's 0, you have viscosity of the oil, then you start to increase, and then you start to decrease until you reach 1, which is the viscosity of the water. Yeah? You remember that? So in this case, we are going to use that equation to calculate the viscosity of the mixture. Okay? And this is a big issue for Peregrino. They have to inject the emulsifier to avoid the formation of this emulsion. Then, so that's a plot, and here I'm plotting it in log scale. So you can see it goes from that was the viscosity of the oil. It's 0.1. I think that's in Pascal. Okay, viscosity of the oil is 0.1. So that means how many centipoise? 10, is it? Yeah, 10 centipoise. Okay, and it goes all the way to almost 1,000. Okay, almost goes all the way to 800. For the inversion point is 60. Yeah, we are operating in 20, so we should be expecting a viscosity of around, yeah, maybe like 30 centipoise, something like that on the pump. Okay, then that's the data for one stage of the pump, and I made the homework for you. I just have the collection of points that's made for water, single stage. So I calculated the coefficients. Remember that we can represent like a polynomial. Okay, so these are the coefficients of rate versus head, and also the same thing for efficiency. You see efficiency, not exactly like I painted. They have different shapes. And that's how it looks like the curve for the pump head versus rate for water. Okay, for different frequencies, and you have the minimum rate, the maximum rate line, and the best efficiency line. Okay, and that's using just the equations that I told you. I put the number of stages that I have, and then I change the frequency 60, 50, 40 using that. Remember that it was okay, that equation. Yep. Now, but when you have viscosity, it doesn't behave like that. But remember, it will be reduced. Okay, it will be reduced the performance, and also the minimum and maximum lines will be moved to the left. So in that case, I have made the calculation for you using the procedure of this hydraulic institute, and for a viscosity of 10 centipoise, I get this plot. Okay, here you have the original. So let's copy that. Okay, see, that will be the original. Okay, with water, and that will be with the viscosity of 0.1 Pascal per second. Okay, you see that is significantly reduced. So the area that I have to operate is this map here. Okay, someone else chose a pump for us, and then we just have to verify if the points they fall within the plot. Okay, and if you want to know the details, you can go to that sheet and change and see how it is calculated. But I had to generate, remember, Excel to plot, you need a collection of points, and I need to change the frequency and also the viscosity. Has to be an input. That's not so important for you. It will be like the expert did that. Yes, so now let's do for the first year. Okay, we are going to assume to avoid complexity, because what happens if the viscosity of the mixture changes with time? Okay, changes. Okay, if I say that the water cut, really I kept it constant. Okay, but in reality you saw that the water is actually increasing, right, from this plot. But if I make it like that, then the viscosity will change, and if the viscosity change, I have to make a map for every year. Yeah, that clear? That's what you're going to get in the exam. No, just joking. But you will get a different map, so you cannot plot all the points in the same map. You have to make a map for every viscosity for every year. Okay, so that's why, to simplify, we say we just have the same viscosity. Okay, so let's first calculate the. So we need average density. So that, I think I have a function called average property. Okay, and here I need the property, the water cut first. Okay, I just have so just one another assumption I'm making in this exercise is that QO is equal to QO local, and Q water is equal to Q water. Okay, that means that really is so heavy the oil, and there is almost no dissolved gas. Just to make it simple, okay, to avoid changing from local to from standard to local conditions. Okay, so here will be average density, average property. Okay, and then that will be the water cut, the property of the oil, and the density of the oil. I have it up here. I block it. Okay, and the density of the water. Okay, and that's just making a volumetric average, like I think we discussed before in class. Rho of the mixture equal to alpha of water, rho of water, plus 1 minus alpha of water, rho of oil. Okay, and we are assuming that the Q, so Q oil, Q water over Q oil plus Q water equal to Q water over Q oil plus Q water. An assumption to make your life easy. Now, the effective viscosity, for that we need to use this Richardson. Okay, I gave you here this emulsion behavior. So for that, I think let's see Alt F11. How did I call it? You go to emulsion and Richardson emulsion. If I'm above the cutoff value, this 60%, then I use the exponential equation for the oil, and if I'm below, I use the exponential equation for the water. If you remember, the Richardson was the viscosity of the mixture equal to viscosity of the continuous phase times the exponential times a constant times the volume fraction of the dispersed phase, right? And then I say I apply one equation for the left side of the inversion point, viscosity of the mixture, use one equation here and one equation here. Okay, two exponential. So let's use that equation for to calculate the viscosity, and that will be Richardson. And Richardson wants viscosity of the oil, so that will be this 0.1, and I have to freeze it. I'm also assuming temperature doesn't change much and pressure doesn't affect much the viscosity. Viscosity of the water as this value here. Then alpha of the water is the water cut, right? Then the exponent for the oil, that's 3.215. I also block it. And the exponent of the water, it's this one, 13. And the cutoff is 60%. Okay, so that gave me an increase of, just to make quality control, that gave me an increase of 30%, more or less, in the viscosity. Just because of this emulsion behavior. Okay, now I have to start moving. Now I have everything I need. I have the density, I have the viscosity, and I have to move now from reservoir pressure, co-current to bottom hole, co-current to the suction of the pump. So first, which equation do I need to use? IPR, okay? So here I hope I call it IPR, PW, what I want is the PWF, and here I need the total, okay? That J, if you see, is for total liquid flow. So I need the total rate. I need the J, the productivity index of the reservoir. I block it. And then I need reservoir pressure. Okay, 110. Okay, here I calculate just Q oil. Q oil will be Q total times 1 minus the water cut, right? Is it? And then I say Q water is equal to that number times the water cut. Yeah, so I'm producing very little water and more oil, which makes sense. Now I want to move from from the from the bottom hole. Okay, where was our okay from the bottom hole all the way to the suction of the pump, and that will be just flowing pipes. Okay, that will be just single phase flowing pipes, but using this viscosity of the mixture, because that's how we represent emulsions. Okay, like one uniform homogeneous fluid, but that exhibits this mixture of mixture viscosity. So for that, I think I'm not sure exactly how I call the function. So let's see back. What do we have? Single phase hydraulic on that module, and it's called P in. That's not what we need. Okay, we want P out because we are moving co-current. So let's see if we have another function called P out. Yes. So you say I need the rate, I need the internal diameter, I need the density we have, viscosity we have, length we have also. Theta is the inclination angle with respect to horizontal in degrees, P inlet, and the roughness. Okay, so I think we have everything. We can try to. Okay, and the way it works is just using the friction factor, just like what you have learned in in your studies. Friction factor, Moody diagram, etc. So that will be P out, and let's see if we have everything we need. Total rate, that number. I don't want to block it. Internal diameter. Initially I have flow in the casing, so it's very big, the diameter. I block it. Then I have the density, and that will also remain constant, but in time it might change. Viscosity, in my case, remains constant, but I also could change in time. Length of that section will be h1, right? I block it. Theta is the inclination angle, and we are going to assume, just to make it simple, that it will be just vertical pipe. So it will be 90. P at the inlet is the bottom hole pressure, and the roughness, we have it here, tubing roughness and lines. Yes, and I block it. So I hope I didn't make any mistake. We will see soon enough. So we got 75.7 pressure at the suction of the pump, and if you see here, the pressure, the bubble point pressure is 30. So we are well above that pressure, and that's actually what we want, okay? That it will be above the bubble point pressure. Now we stop there, our calculations, and we go from the wellhead, where we have 10 bar or 7 bar, down to this discharge of the pump, okay? And from there, really, remember, it's just flow in the tubing, okay? So we just could use just flow in pipe, and we had one equation that was P, what do we need? P in or P out? P out, are you sure? P, we have, okay, P1 is discharge, P2 is wellhead, okay? We have wellhead, so we need to move counter current, so it will be P1. So P1 is P in, and so let's see, I need the rate, I need the internal diameter, that will be this number of the tubing. Then I need the density, that might change with every year. Viscosity, length is that number here, and I block it. Again, we're going to assume it's 90, the angle, and P out will be wellhead pressure. And what else do I need? The roughness, and I also have to freeze that. Okay, and it tells me that I need to flow 188 bar at the discharge of the pump. Yes? Okay, so then I say the delta P of the pump has to be the discharge minus the suction Okay? And then I can calculate also the head. And the head is, if you remember, delta P divided by rho by density, but it's not only by density, but it's by gravity, gravitational acceleration 9.81. Okay, but remember, to make consistent units, the pressure has to be in Pascal. So that 1 e to the 5. Yes? Okay. So we have the pair of delta H versus Q, and then I go to I have to make sure to use the right viscosity. Okay, so I have to take that number, 0.138 and 910. I go to my sheet where I calculate the performance map for viscous fluid for the pump, 138 and 910. Okay, and that's how the map looks like, and that's the first point. Okay, it's already plotted there for you. So you see it is exactly in the center, almost in the center of the diagram. So I should be able with no problem to produce that point. Okay, one question: what speed, what the rotational frequency do I need to produce that rate?
What speed or what type of speed?
Remember that we need, okay, let's so that's what we got for the first point. Okay, so that was Q equal to 17 standard cubic meter per day. Delta P was close to 111 bar. Okay, and the viscosity was 0.138 pascals per second, and density was 910 kilogram cubic meter, right? And we know that that line is for 60 hertz, right? Here I think it's written. That's for 60 hertz. And that line here is for 45 hertz. Okay, we have it up here. And then that line here is for 30 hertz. Okay, so that means that to produce that rate, I need to be, how much is it? 52.5, right? Okay, so frequency, operating frequency has to be equal to 52.5 hertz, okay, or around that value, right? Yeah. Should we go to the next point? That clear how we did? Just the same thing we have been doing since the beginning of the semester. Available and required. You see how powerful it is? You can use it for almost any task okay, so now let's see okay, what happens when we go in time. Can we just drag this? Okay, no, first, okay, so we verify it falls in the map. It's not greater than the maximum rate, and it's not lower, so it's within the operational envelope, which is this one. Okay? But then what else do we have to check? If you remember all the constraints that the pump had. One was that minimum and maximum rate, right? Inside the envelope, looks fine. Then the other thing is suction pressure has to be greater than the bubble point pressure. Okay, what else? Maximum power, okay? We have to be sure that we can pump that rate. We are not sure yet. So how do the power is delta P times Q times over the efficiency hydraulic and the mechanic efficiency. Okay? And we said for this guy, someone chose that pump. We had no control, but it was 760 horsepower, what is installed there. And I need the efficiency. So the efficiency, I think I fit it also a polynomial if you go to the end, you have the efficiency, you have the polynomial, and then you have an equation that if you go to ESPs, okay, pump efficiency. So that I have to give the rate, the frequency, the reference frequency, and all of the coefficients that I just found with the trend line. Okay, so let's use that equation. Okay, hydraulic efficiency is going to be equal to pump efficiency, and pump efficiency wants to have the rate, which is the total rate, the frequency, which was 52, okay, point something, 52.5 approximate. Reference frequency that I have here is 60. That curve that I showed you was made for 60. And all the coefficients, that will be A5. I have to block it, okay? Remember, F4, A3, A2, and A1. Okay, and it gives me an efficiency of 74%. Okay, it's a miracle that gave. Okay, usually we have some bugs in class, so okay, 74 for that point. And now I can calculate, I have the mechanical efficiency, and I can calculate the pump power. And that I do by saying delta P times 1 e to the 5, okay, to have consistent units, to have it in Pascal, times this number, the rate, and I want to convert it to, it should be in seconds, right? So I have to divide by 24 times 300 and 3600, right?
Yeah.
Okay, what else I'm missing here? Delta P, Q, and then I need the efficiencies, of course, right? So the efficiencies will be that number, mechanical efficiency, frozen, and then I have the hydraulic efficiency, frozen, no, not frozen, but I have to divide by 100. Okay, I think the keyboard died. No. Divided by 100. Okay, and that is in watts, I think, right? You're exercising all the engineering that you have seen in the last years. Yes, and so that will be in watts. And what is the conversion between watt and horsepower? 700 and something. Power. So where is power? Power. So from watt to horsepower.
Multiplied by
0.001 something. Okay. And that times that number, 400 horsepower. Okay, that means good, we can produce, we are safe. Now it took a lot of effort and we're almost towards the end of the class, but now the nice thing, if I didn't make any mistake, and you just drag and take it down. Yeah, so let's see what happens for the other years. This one should remain constant, this one. Okay, here I have a problem. Okay, Okay, here I should put one more that will be frequency, and here it's 52.2. Okay, so if you see, everything goes fine, but here at some point you see that suction pressure falls below the bubble point. Okay, which I cannot have. So the only solution, what is then?
You solve it?
Huh?
A solver?
A solver for what?
For pressure?
They're getting addicted to solver.
Force pressure to
That's
zero?
good. So you want the pressure to be above the bubble point. Yeah? And by that you're going to change. What is the only thing we can do? Reduce the rate. Okay? So in that case you will have, you will have to go back to your, but there's something, why this is 79 here? Okay, because of the, yeah, I think here there is something wrong. Things should be like that. And these two I can just delete. Okay. So flowing, okay, it's from year, when I have a reservoir pressure of 175, I have to say, sorry, reservoir engineer, you cannot produce that rate, because otherwise we will have a very important constraint, which is gas will start entering into the pump. So what we do is we use the solver, like Alexander said. Where is data, solver? Okay, and I had it already pre-filled for you. Is F, what is F? No, that's not. Let me just delete all of that. Okay, so I want to drive that value exactly to a number of 30. Okay, that was the bubble point pressure, and changing the rate, that number here, and yeah, let's see if it, yeah, and now the rate has to be reduced to 1554. Okay, and of course I want to be producing as much as possible. I can produce less than that, but then I will be losing production. Okay, but really, to be on the safe side, what we can say is, say, required pressure at the inlet, at intake, pump intake. Okay, and that will be the bubble point pressure times a safety factor. We can say, for example, 1.2 and 36. And then we say, well, we don't want to be, because of all of this cavitation issue, and we can have losses inside, and we can have the gas liberation, so let's say a bit higher than that. So we are going to solve again, and now has to be 36. Okay, and then I apply it for all the others. That will be 21 here, and again 22 and 22. Okay, and so far we don't know if the pump is able to deliver, okay, because we don't know, we haven't calculated the power. But you see that the efficiency is changing slightly because the rate changed. And let's see the map. So you see how the points go increasing, and then after that they go to the left. Okay, so which points are feasible and which points are not? Very clear. Okay, we are just finishing class. This is the last effort of the class. Wait. Okay, so all of these points are feasible because they are within the envelope that I have, that is this one, if you remember. That point is just in the border, so that one won't be feasible to produce. Okay, so I have to bring it back. And how can I bring it back? Reduce the rate, but if you reduce the rate, you're going to pull them more to the left, right?
Increasing the edge.
But if you increase the rate, you're going to get this bubble. So how do you bring back this point?
Reduce the pressure.
Yeah. Well, let's go back to that later. So, well, later, no, in a few minutes. So let's write first the frequencies for those. So that was 52. That will be how much? That is 7.5, right? So we divide by 3. That gives how much? 2.2, 2.5, right? So that will be 52.5. Then the other one will be 55, 57.5, right? 55, 57.5, and then, yeah, maybe 57. So let's write those frequencies here. You remember? $55, 57.5, and here that I think the efficiency, I think should take that number from here, right? Okay, and then I can drag it and calculate the power. Still the power is okay for those 3 years. So now let's see for the last year. What is the frequency of that point? We can say 56 maybe. Yeah. $56, and then I drag down. I'm okay, safe with the power. So that pump that I have will be at least able to pump the first 4 rates. But now what happens with the last rates? You have the if yeah we so how do we put those points back into the map? Well, the answer is you cannot. Okay? Because if you reduce the rate, okay, the delta P will be less, so your point will be here, but you will still be outside of the envelope. Okay? So at that point, no matter what you do, you won't be able to put the point back into the envelope. So that the only option is to go and change the pump. Okay? Just because there is no way. If you reduce the rate, you increase the rate, you're locked because of all the operational constraints that you have. So at that point, you have to think, if it's after 5 years of production, you have to think about changing your pump, the model of the pump that you have, for a different model. Okay? Or if you want still to operate with the same pump, then you have to find a pump that has a bigger envelope. Okay? That at least if you know, because at that case, you know that your problem is the suction pressure. That you cannot go below that because of the suction pressure, above that rate because of the suction pressure. So in that case, the only solution is to find a bigger pump. Okay? Any question before we close? So just to summarize, what I want you to take, equipment, when you put equipment in the system, it has a lot of operational constraints, and it depends on each type of equipment. Depends if it's a pump, depends if it's a choke, depends if it's a beam pump, depends if it's a gas lift, etc. It has a lot of other constraints that you have to take into account when you design your field. In this case, a particular case of the pump, it has an operational envelope that will change depending on the viscosity. Okay? And then you have the other constraints, which are the suction pressure of the pump and the total power. And you have to fulfill all of them such that your operational points will fall inside the operational map. Okay? And sometimes you cannot with the same pump for the whole life of the field, so you have to change it. Yes, so we close the session. See you next Tuesday. Okay.